What? You want to learn about chemical composition? Good. I was hoping you would. I rolled my sleeves for this one. It's a good one. It's a good one. Review. No, we got to keep going. You review on your own. All right. What we are going to look at now, knowing what you know from chapter 2 in terms of basic math and conversions and moving back and forth between this stuff. Chapter 3, how you know atomic structure and the periodic table and what all this stuff means on the periodic table, how it's organized, what the numbers mean. From chapter 4, which was, what was chapter 5? That was the same thing. It was all that together. 3 and 4 was together. Chapter 5 we just did with naming. So you're going to take all of this now and start to integrate some things together and talk about chemical composition, finding out what stuff is made of, how much of the stuff is present in these samples, etc., etc. Okay? You can read this yourself. You know that this is to be true. These elements that you see on the periodic table are not things that are just sitting out there. Generally, these are the basic different types of atoms that exist. Very seldom, except for like oxygen and nitrogen and hydrogen, but very seldom will you find them in pure elemental form. Carbon you'll find that way too sometimes. But a lot of times you're going to find them mixed in with other things. They're going to be bonded with something. They're going to be trapped up in different types of molecules. Now you can extract individual ions. We'll actually do that in lab. We'll pull out ions from a solution. We'll pull it out from a solid. We'll separate these things. Okay? Take, for example, copper that's in a solution and extract the copper and solidify it and make solid pure copper. Okay, that's one of the labs that we'll do. Okay. It says to know the amount of a material in a sample. So if you have a sample of anything that you see up here, and you want to know how much of a certain material is in it, how much of this molecule, whatever, you need to know what fraction of the sample it is. In other words, if this is a, say this was old school and this was Freon, okay, instead of the new stuff. Say this was a Freon container, or sodium chloride, salt. You would have to know, if I wanted to know, for example, how much Freon was in this can, you've got to realize that you can't say 12 ounces. Because 12 ounces was how much the total of everything there that is in the can. That doesn't necessarily mean that it's pure Freon and you've got 12 ounces of Freon. It could be that you have like a 0.1% solution of Freon in that 12 ounces. So 0.1% of what you see there is probably what's going to be Freon. This kind of math and this kind of reasoning, trying to figure out that kind of stuff, is where we're going with this chapter. Okay? Some applications of this, why it would be important. You like in food chemistry especially, how many calories can you eat? What's a normal diet? So come up with these tables or Weight Watchers points or whatever that add stuff up. You eat certain things. It's made of this much of this chemical, so you can only eat so much of it. That kind of thing, and then it all adds together. You know, for example, we're going to answer a question, I think something similar is like, you know, the salt packets that exist. How many salt packets, those little tiny ones you tear open, can you eat on a daily basis and still stay within your sodium intake for the day? Now, I'm talking sodium intake. I'm not talking sodium chloride intake. You know, realize that a sodium chloride molecule or formula unit is an Na and a Cl together. So you got to realize that all of the weight that you are eating of the salt, not all of it is the weight due to sodium. Some of it's the weight due to chloride. So how do you figure up how much actual sodium consumption is occurring? Okay? So how many of those packets can you eat if you just want to eat them for some reason? The amount of hydrogen in water if you're going to make hydrogen fuel. You know that if we talked about electrolysis and how you could pass a current through water, split it into hydrogen and oxygen. Well, realize that by weight, water is mostly oxygen, right? There are actually, by number, there's 2 more hydrogens than there are oxygens, but when you start collecting hydrogen, the weight becomes very small because they're very small atoms. So how much water would you have to decompose to get a certain mass, a certain volume, whatever, of hydrogen? Okay, we have to be able to answer these types of questions. Someone certainly does. Otherwise, we can't go out there and buy it and get it and use things. All right, so here's what we got to realize, is that when we're dealing with counting things like this, the numbers that we have to deal with are just astronomically huge numbers because atoms are so tiny. And if you have like one nail, for example, the amount of iron atoms in that one nail is just ridiculous. There's so many iron atoms in there. So it does not seem efficient at all to try to say and count and write out the actual number of them that are there. So what we do is use research that has already been developed, use the knowledge that you already know about the periodic table, how much things weigh. If you know how many of them you have, how much each atom weighs, you can indirectly use some math to figure out how many of them are there, right? Like if I told you that each basketball weighed, I don't know, a certain amount of pounds. I don't even know how much they weigh. Say 2 pounds, that's whatever. Say a basketball weighed 2 pounds. And I had 60 pounds. I had a set of basketballs that weighed 60 pounds. You could figure out how many basketballs there were there, right? You would take 60 divided by the fact that each one weighs 2, and you know that there's probably 30 basketballs there. This is the same type of thing we're going to be doing here. Okay? One way to count nails, for example, is by the pound. Anyone that's ever done a project and had to go to the hardware store, generally, at least old school, now you go to Lowe's, you buy them in boxes that are already made. But if you go down to the good old True Value hardware store downtown, you still got the bins where you scoop them out and you weigh them on the scale, right? That's the way you're supposed to do it. You actually count your nails by the pound. I know that if I'm in a project, I don't sit there and count up how many nails I'm using. I don't say I need about, pound and a half of nails. However, using this type of reasoning, we can actually turn that mass quantity into an actual number, because then all that we have to know is how much one nail weighed, right? So if I knew the mass of them and I knew how much one of them weighed, then you can start turning that into actual numbers of the nails present. So how do I know how many nails I am buying when I buy a pound of nails? Now, I know this doesn't seem like chemistry, but I promise you it will relate. Let's use this example. Because another way to think of this, similarly, is how many atoms are in a given mass of an element. If I have a pound of nails, how many nails are there? If I have a pound of sodium, how many sodium atoms are present in a pound of sodium? Okay, I'll show you. All right. Let's use this one. Let's keep it simple for a second. Relate to something we know. A hardware store customer buys 2.60 pounds of nails. A dozen of the nails has a mass of 0.150 pounds. How many nails did the customer buy? Now, what I want you to do as we go through this math is don't try to do this in your head. And the reason is because when we get into the chemistry, it's going to be very difficult to do in your head. I want you to set them up using conversion factors that I've already showed you with the first couple chapters that we did. All right, what do we know to be a conversion factor? And what is our starting point? That kind of thing. Do we have anything that we can use as a definition, two numbers that are equivalent to each other that we can use as a conversion factor based upon the statements that you see up here? That's right. We know this and this. We say a dozen of the nails has a mass of 0.150 pounds. That is a conversion factor. One of those can go on top, one of those can go on bottom, and it doesn't matter. It depends on what units you're trying to cancel out. Okay? That means you can start here with this number. If you have 2.60 pounds, and you know this conversion factor to be true, that for every 0.150 pounds, for every dozen that you have that weighs 0.150 pounds, you can then use that, and the pounds can cancel out. Okay, I'll show you. You're going from pounds of nails. This is what you got right here. Okay? You're going from pounds of nails to dozens of nails, and then you can convert dozen into an actual number. Because if you have 2 dozen, you have 24, right? You're going to see that this type of math, this type of reasoning is what this chapter is sort of all about. Okay, how am I going to go from my pounds that I have, 2.60 pounds, how do I go from pounds to dozens? Well, I use this right here. Okay? I know that 1 dozen nails weighs 0.150 pounds. If I did this math, if I ignored all of this over here, and I was just going from here to here, this pounds of nails would cancel out. My answer would be in dozens. I would be done. Okay? Now, I don't want to stop there. The question asks further, I want how many actual nails did the customer buy? Realize that when you say the word dozen, you're using a grouping for an actual number. That's not the actual number. It's representative of a certain number. A dozen represents 12. I want the actual number here. So what you know then, I know that you can do this in your head. I know that you would get there and say, okay, well, this is easy. All I got to do is multiply that by whatever or divide it by whatever. I want you to do the math so you don't get lost in the future. Put a dozen nails down here. It's 12 nails on the top. These will cancel out, and your final answer will be a number of nails. Does anyone have a problem following that right now? I need to know if so. I'll go over it again. That was me. It sounded like my ring. All right. So, there's your pounds that you're buying. You know that this is true. For every dozen, it weighs that much. Now, you can string these conversion factors all together. Okay? I could stop there. I could get an answer. I could bring it down here and then do this step. It doesn't matter. You're going to get the same answer. So let's string it all together. Then I also know that 12 nails are equivalent to 1 dozen. So this cancels. That cancels. And as long as I have the right unit left, you should be in good shape for your answer. So in this case, they bought 2.60 pounds of nails. And for the particular size that he or she bought, they received 208 nails according to your calculations. Okay? So you counted it by weight. All right. Now, if I had 2.60 pounds of these nails, and I had 2.60 pounds of these nails, would I have the same number of nails? Why? The mass is bigger of these, okay, versus those. So to accumulate 2.60 pounds, I would need more of these, right, than I would of these. The same thing applies to atoms. Look at the masses of these different types of atoms. You will see that some are much larger than others. Take the water example, hydrogen and oxygen. To get a pound of hydrogen, you're going to have a whole lot more atoms of hydrogen present than you would to get the same amount of oxygen, okay, the same poundage of oxygen, if we measured it like that. So keep that in mind. Okay. So the question was, would the mass of a dozen be 0.150 pounds? First of all, no. If you bought a new set of nails, the mass of a dozen would change according to that particular thing in question. So same thing with atoms, if you picked a different atom. So the answer to would there be 208 nails in 2.60 pounds, the answer is no. How would this affect the conversion factors? You'd have to make a new conversion factor. You can't use the same one that you just used. You would have to make a new one. Okay, now this brings us to, anybody take high school chemistry in here? So you know all about moles. You've heard this word before. Okay. Well, it's pretty simple. A mole is the chemistry version of a dozen. Okay, no, it's not that little guy that runs through your yard and tears the crap out of everything. The mole is like the dozen in the sense that it represents a certain number. A dozen represents 12. A mole represents much, much more than that. It gives us a way to take bulk counting and make it easier, just like a dozen does. Okay? So, it says if we can find the mass of a particular number of atoms, we can use this information to convert the mass of an element sample to the number of atoms in the sample. Basically, just like we did with nails and that kind of thing. Now, the number of atoms we will use, instead of like our version of the dozen in chemistry, is this big number here. 6.022 times 10 to the 23rd. So that means take that decimal place and move it 23 places to the right. It's a big number. What we say is that many of anything is a mole. Okay? So whether you're talking about elephants, cars, atoms, it doesn't matter. A mole is that many. Okay? So we call this a mole. 1 mole, this is a conversion factor now. 1 mole is equal to, like 1 dozen will be equal to 12, 1 mole is equal to this many things. Okay? There actually is a National Mole Day celebrated by chemists. Anybody know what date it is? What is it? October 23rd. That's right. So, I got a t-shirt. On the back of it, I do. It's too small now or I'd wear it, but it wouldn't be a pleasant sight anymore. It's actually, you know how you get like numbers on the back? You know, the number on the back of this shirt is that one. So it's cool. Yeah, it's cool. It's got a little mole on the front. Says I celebrate National Mole Day. Don't lie. All of you want one. I told you, everybody's a closet dork, whether or not they want to admit it or not. You just don't want to admit it. That's all. Do what? That's right. That's right. Okay. I used to have a sheet that was kind of neat that I passed around. It said like 1 mole of this would be this. I forget what it was. Like if we had like I forget what it was. Like a mole of money. Like if you had a mole like that many dollars, each person would have like so many trillions of dollars on the entire planet. I mean, this is a big, big number. Anyways, so moles are going to be our little packages of chemicals that represent that number. There's that many of them. Okay. Now, if you don't care about this, then don't worry about it. But how this mole came about. Anybody know who the guy is? 6.022 times 10 to the 23rd is called somebody's number. Avogadro's number. Okay, Amadeus Avogadro. Quite the striking, handsome man. You should really take a look at him sometime. Google Avogadro and find an image of him. He kind of looks like an alien. He's got like an inverse teardrop head with these giant eyes. He's a real classy. Anyways, carry it in my wallet. It's like, hey, here's my favorite scientist. You want a picture? That reminds me. Never mind. No. I used to teach high school, and there was a relatively rural population of people at the high school. And nothing bad. I'm thinking Chad Rusher. You remember Chad Rusher? He would carry around, and I was thinking about things people carry in their wallet, like pictures. And people carry their family and their girlfriends. And he's got the giant catfish that he caught. He pulls it out. He's like, "Hey, check out my catfish!" And he pulls it out and shows it to me. It's like, yeah, that's awesome. That's what you should carry in your wallet. Yeah, awesome guy though, man. I love that kid. Anyways, a mole, how it came about was it's the number of particles equal to the number of atoms in 12 grams of carbon-12. So if you had pure carbon-12, like on the periodic table, and you had actually 12 grams of it, Avogadro determined that in that sample, don't make me explain the experiment, in that sample would be that many, 6.022 times 10 to the 23rd atoms present. Now this is going to be very, very important. And the reason that it's important is because what it allows us to do, see this? It allows us to go to grams. It allows us to utilize two things. I'm going to explain this in a second, but I want you to look at the periodic table and look at, for example, lithium. It says 6.94 for the molecular weight of lithium, right? That means that one atom of lithium would have an atomic mass in terms of AMUs of 6.94. Here's what also is very, very useful about this because of what Avogadro did. We also know that if we have 1 mole of lithium, if you had lithium, those lithium atoms and had 6.022 times 10 to the 23rd of them present, and you put them on a scale, it would weigh 6.94 grams. So that's very, very useful. That allows us now to count things that normally we wouldn't be able to count because of this. I know if we don't understand it, just realize it's very important that he was able to take a gram value and associate that with a number value. Okay? Yes. There's 2 different ways to look at that number. One is AMU of that atom. Another is, that's what's called the molar mass of that atom. If you had 1 mole of it, that's how much it would weigh in grams. It's the same value, so it's double dipped. It means 2 different things. Okay, it's very useful. Okay, so 1 mole of carbon-12 weighs exactly 12 grams, as indicated by the table there. Okay, so we said this was Avogadro's number. So 1 mole of carbon atoms weighs 12.01 grams, and there would also be, because there's 1 mole, this many of them present. Okay? Okay. Huh? This is the number of, if I had 1 mole of carbon, what that means is I have this many atoms of carbon. That's what that means. If I had 1 mole of pure carbon, and the only atoms present were carbon, I would have this many of them. And if I could take that 1 mole, set it on a scale and weigh it, it would weigh 12.01 grams. That's what this is saying. Okay? Now keep in mind at the same that's exactly right. Yeah, they're extremely tiny. The average mass of a C atom, carbon atom, in AMU Okay, that's like proton-neutron kind of stuff. Remember, go back to that. 12.01 AMU. So these numbers agree, but the units are very different, obviously, between what we're dealing with here. So, okay, let me do an example or two before we get out of here. So, oh, come on. I know that that's slow, but I also start 5 minutes late. So, hey, I'm not keeping you here. If you need to go, go. But just keep in mind, I got it all on tape. Okay, let's do this one. Okay, and then we'll quit. A silver ring contains 1.1 times 10 to the 22nd silver atoms. Don't worry about how I came up with that. Just say that you know that. Okay? A silver ring contains that many silver atoms. I want to know how many moles of silver are in the ring. You only need to know one thing. You need to know the definition of a mole. Right? 1 mole equals 6.02 times 10 to the 23rd. Okay, we can set this up and we can do it. We're going from, we know this conversion to be true. Okay, this is our definition of a mole. We're starting with this many atoms of silver. So I'm going from atoms of silver to moles of silver. How do I do that? I use my definition of a mole, the conversion factor. I know that if I put 1 mole on top, that's equal to this many of anything, in this case atoms of silver. That'll cancel out, and I'll get an answer in moles. Okay? So now I just plug in my numbers, so that end up being divided by that, and they cancel, and you get 1.8266 times 10 to the minus 2 moles of silver, so pretty small number, right? Now we got to keep in mind sig figs here. We've got 2 here, 4 over there, so we're going to be limited to 2. 1.8 times 10 to the minus 2 moles of silver. Okay? Check it. Make sure. How can you do that? The reasoning here says the units of the answer, moles, are correct. The magnitude of the answer makes sense since 1.1 times 10 to the 22 is less than 1 mole. We know, for example, you know that this number has to be less than 1. And the reason is because a mole is 6.022 times 10 to the 23rd. This is times 10 to the 22nd. It's actually a smaller number. That's what this is saying. So the fact that it's actually less than what a mole definition is means that your number should be less than 1 over here, and it is. All right. We'll stop there. Make sure